Here we go again. But this time I got the record button hit. So 11.3 combinations. This is the last series for tonight's lecture anyway. So hopefully you had good success with 11.2 with permutations, working through them. And if you did, then this one on combination is going to be pretty straightforward because it's basically doing the same thing except with one sort of slight change. We're going to divide out the number of repeats that are caused between the difference of order being important, or second, third finger, and order not being important. So see, these are the same three fingers, but they're in different orders. So if I don't look at ordering, this is one set of fingers, whereas if I look at order, there's three. So we have to divide out the extra, the ones that are really the same group, but in a different order. So let's see what that means. So as we look at combinations, we need to be able to tell the difference between a situation that requires a permutation, order important, and one that requires a combination, order not important. We will then solve some problems involving combinations and the combination formula. And again, we'll be able to get by without that formula as we come to understand it, just as we did with the permutations. Okay. So first of all, a combination is when items occur they're selected from the same group of things. Just like a permutation, no item is used more than once, just like a permutation. But unlike a permutation, the order really makes no difference. So I might have a committee of people, they're all equally empowered, they've got the same roles. That order is not important. But if I do an executive committee, president, vice president, treasurer, then the roles are different, and the order that those people are placed into those roles makes a difference. Okay, so permutations, order matters, combination, order makes no difference. So once we decide which, and we have to do it from the context of the problem. Once we decide that, then we proceed one of two ways. So this question, does it involve a permutation or a combination? 6 students are running for student government. They have a president, vice president, and treasurer. Order seems to be important already. The student with the greatest number of votes, so there's an ordering mechanism, then whoever has the most votes becomes the president. So it must be like a higher position, right? A different position, an ordering of position, second voter. So I'm going to say this is definitely permutations, right? There we go. It is definitely a permutation. Order is important. And you'll see this next one, look at, they just need a 3-person committee. No assignments of roles or duties, no voting for them. They simply, out of the 6 people, 3 people are going to be on this committee. This is the definition of a combination. Okay, I have Fred, Joe, and Sally is the same thing as having Joe, Fred, and Sally. The ordering doesn't matter. They're all 3 in there. So those are all the same 3 groups. So let's see how that works. So let's say I need to arrange the 4 letters A, B, C, D. But I tell you that it's really not important how we order them. But if we were to do permutations, ordering is important. And so you look at this group. Permutations, each one of these is separate, but you notice each of them contains A, B, and C in various arrangements. So if order is now not important, this is not 6 groups, 1, 2, 3, 4, 5, 6. It is only 1 group. And the same thing with each of this. Permutations, these are all considered different, but under combination rules, they are all the same group. They have A, they have D, they have B, various orders, so forth and so on. So combination, this would be 4 groups. Permutation, it would be this number, which is 6 times 4 would be 24. So what we did is, notice this, a permutation for permutate 3 is what we did up here with all these, when order is important. So that's 4 factorial divided by 4 minus 1 factorial which gives us 4 factorial over, wait, no, 4 minus 3, right? That's how it goes, that's how it works. So that's over 1 factorial. So it ends up being just 4 times 2 times 3. 3 times 2. The order doesn't matter, but let's just do that. So that's 6 times 4 is 24. Well, we count there. But if we say order is not important, how many different ways are there to order this, each one of these? There's 1, 2, 3, 4, 5, 6. That's 3 times 2. That's 3 factorial ways to organize this. So when we think down here of this being a combination, we take the permutation, 4 factorial over 1 factorial, and divide it by 3 factorial. 3 factorial is 3 times 2, which is 6. So what we end up with is 24 divided by 6 is 4. So we're going to see how that's directly results in the new formula for combinations. So combination, think of it as a permutation, and then you say, hey, order's not important. Let's divide by r factorial. That's all there is to it. So you see here, this part is the formula for permutation, right? And then we divide by r factorial because that divides out the ordering of each of the groups. Each of the groups that would be considered the same if order is not important. Okay, so here's one. We're selecting 3 people from 8 people. So 8, 3. Again, we get 8 factorial, 8 minus 3. So this part would be what we would get with a permutation. So 8 factorial over 5 factorial, right? You know, the 5 factorials cancel. 8, 7, 6. This part is the new part. We're dividing out the ways you can organize 3 things, arrange 3 things when order is important. 3 times 2 times 1. So 3 times 2 times 1 is 6. That cancels. So our final answer is just 56. Had this been a permutation, we would have multiplied by 6 and got a larger number. Okay, that's all we have to do. But we have to see that this is a combination because they want committees. Now that's one of the things you're going to have to do. In each section, we focused on permutations on one section, combinations on the other. But as you look at this in the real world setting, they can be a mixed. You can have one situation where it is combination, one where it's permutation. You have to be able to decide, is ordering important? Okay. Here's another example, and it'll be our last one. We've got the U.S. Senate had 51 Democrats, 47 Republicans, and 2 independents. I think it's kind of close to that, but maybe reversed at this point. How many distinct 5-person committees can be formed if each committee, so 5 persons, 3 Democrats and 2 Republicans? Well, wait a minute. This seems unfair. Where are the independents? The independents don't even get a chance to be on this committee. That's bogus, I think. Maybe because I'm an independent myself. It's great to be part of a party, sure, but our government's also founded on independents who represent the people that they're in, not I won't get started. But anyway, very unfair. Independents are not being considered. So for this one, we have to go, remember, these 3 Democrats are getting chosen from the Democratic group, which is 51. So we're going to get a combination. I'll just click on here. So the order doesn't matter, but it's a combination. So first thing we have to do is get the 3, well, not necessarily first, but we'll do it first. 3 Democrats out of 51. So out of 51, we're going to choose the 3 Democrats. Remember, this part here is the permutation. So I might have gone 1, 2, 3. Okay, we get 51, 50, 49. So that's a permutation. Since order doesn't matter, we're going to divide by 3 factorial, which is 3 times 2 times 1. And now what I can do is 2 goes into 50, so that's 25. 3, I think, will go into 51. How many times? That's 1. That's 2 left over, 17 times. So 3 times 17 is 51. And then we can multiply just these, and we'll get our answer. So that's basically what they did here. We'll get this as our answer. I'm not going to try to do that in my head, but that's what we would get. So you can see we can use the formula for combinations, and at the end of this presentation, I will show you how to use the calculator where you can just enter that in, and if that's the way you want to do it, great. I like still doing this way because it gives me meaning of what we're doing. It's still that idea of a permutation. You know, how many do we have to choose from? And then it gives the adaptation that, oh, wait, order is not important. So let me divide out all the different ways to order three things, which is 3 times 2 times 1. And I think that that's something that's stuck with me. Even being a math teacher, I sometimes sort of forget these formulas, not as much as I used to, but yeah, especially I'm on vacation, haven't done any math in a couple months. Ask me about combinations, I don't know, but I'll remember this. I'll remember the listing. Okay. So then, but we're not done yet to choose how many different ways you can get the Republicans. Again, we've got 47. We're choosing 2 of them. Again, it would be 2 Republicans getting chosen, 47 times 46. But this assumes order is important. Since it's not, we divide by 2 times 1, which is the way to organize 2 things. And what we end up with, and again, that's what they end up with here, right? 47 times 46 divided by 2 times 1. This method just jumps to it. This takes a little longer to get there. Of course, if you're using the calculator, you plug this in and you get there, so that's okay. And then what we do is we use the multiplication, our fundamental counting principle, which I like just calling it the multiplication principle. You just multiply those two, because there's this many choices for the Democratic side. Each one of them has 1,082 different choices that could have happened on the Republican side. So that's still 22 million different committees. And we still haven't included the independents. That's taxation without representation, something like that. And that's it. So we're going to, and this time I had the recording going. I did this once before, so hopefully I gotten better. I know I toned down my political rhetoric a little bit. I didn't. First time I did get on my soapbox, talked a lot about independent versus Democrat and Republican, and I'm just trying to get my calculator to load here. Here it is. That's why. Let me clear out the window because I've already done this, but let me show you how, and we'll just use our 7. We've got 7 favorite books. We're going to choose 3 from them. Now, when it's we're going to put them on a shelf, so the order is important. That's a permutation. The way we get a permutation with the calculator is you go to the math key here. So notice the math key brings up this menu. We need to arrow over to probability. So we go right arrow until we get to probability, and look the magic we get. We get NPR, that's our permutation, and NCR, which is our combination. These are the 2 we're going to use. It's also got the factorial key if you want to do like 7 factorial. But the ones we'll use for this are these 2. Now notice the n comes first. So what you have to do is you have to enter the number first, come back here, get this little doohickey thing, and then put in the last number. So this is the way it works. You put in the 7. For 7, we got 7 favorite books we're choosing from. We hit the math key. We go over to probability. We go down to NPR. We hit enter. And notice there's 7P. And then now we're just sitting there waiting to put in the R. The R was 3. We've only got 3 shells to put it in. We hit enter. That's 210 different arrangements of the 3 books chosen out of our 7 favorite books. Now let's say we're just going to send these off to a library. We're going to send 3 of our favorite books off, so we're going to just put them in. And now the order that, maybe we put them in a box and they get jostled around. Hopefully not, because that might break the books. But the order is not important. That's what we're dealing with. Order not important. We got 7 books. We're going to choose 3 of them. So we go to math, but order's not important. We know that, so we go down to combination. Okay, just like that, we're going to take 3 of those books, send them off, but now order's not important because they're they're packaged in a package, and who knows how they get opened. We've only got 35. So notice it's 210. How many ways can you arrange three things? 3 times 2 times 1, that's 6. Watch this. 210 divided by 6 is 35. So it works both ways. We've got the built-in formulas if you've got a TI-84. Some of you have other calculators that you'll see that has the NPR and NCR. It's got them in there. You're welcome to use those. But again, it's just sort of counting how many things as we arrange them, just like we went through and did. So now it's time for you to do the homework for 11.3, and you will have this complete evening taken care of, 11.1, 2, and 3. Next, we look at 11.4 and 11.5 together, but we'll take on that another day. Be well, stay safe, and enjoy.